Alright, physics students, maybe you've already figured this thing out, maybe not, I don't know. But at any rate, this will be your little instruction time here of how to deal with an object that's on an inclined plane with no friction force and it's accelerating down the ramp. Now, we just dealt with all the elevator type problems, and I mean those aren't gone. We just need to move on and see what unbalanced forces look like in these other types of scenarios. So that's what we're going to do. Hold on, I need a sip of coffee. Okay. Now, first we need a force diagram, because that's what expert problem solvers do. So I'll draw it just right here. And we have a force of gravity here. Oh boy. Oh boy. Force gravity. And then we have the normal force, which some of you still are not drawing very well on your force oh gosh. Get that out of there. That's not very good. Now here's the question. I don't know. I've drawn three different normal forces at this point, and I don't know if you've seen any of them, because I think when I do the undo, it's like it never happened. Maybe not, but anyway, there is the normal force. Now, are there any other forces acting on this block? No, because since we have no friction, I mean, again, we have the gravity force down, we have the normal force pushing perpendicularly to the surface, so other than those two, there's nothing else. Which means, if you think about this, if you were able to, let's see if I can do this without screwing anything up. If you were able to move the gravity force and slide it up here, and it would end up like this, yeah? And then that would result in a resultant vector that's going down the incline. So if I were to, again, slide the gravity force up, oh boy, oh my gosh, up like this, if that was the gravity force being slid up there, then that would result in an unbalanced force this way down the track. Now I got to try to erase this. Okay, there we go. All right, so that's what will happen if we have a force diagram that looks like this. Maybe my normal force is a little short. Maybe my gravity force is a little long. I don't really care. But we do need to do the, oh jeez. We do need to do this. We need to rotate. Oh my gosh. We need to rotate our axes like so. And like so. That's not terrible. Okay, so yeah, because the one is supposed to be parallel, the x-axis is supposed to be parallel to the ramp surface. The y-axis, so this is the new x-axis. This is the new y-axis. It's supposed to be what the normal force is on. So that's our new orientation here. And that means that the normal force is actually on the y-axis. The gravity force is actually on the y, and it's also on, oh my gosh, come on, the x-axis. So we have two different things going on. We have an FGY, and we have an FGX. Oh boy, right where I put FG is the FGX. Why did I do that? I don't even know. FGX. I have a feeling this video is going to take forever. All right, so we have two components here. I hope you're seeing that we have two components. And because we have a 30-degree ramp, that means this is 30 degrees. Hopefully you remember that from before. Now, I'm gonna write down both of the summations, even though we don't need both of the summations for this question. If we look at summation of all the forces in the x, we have what? Hope you're seeing here that literally all we have is the FGX. That is the only force that's acting in the horizontal we have an FGY and an FN that are equal amounts and opposite direction. But the FGX is the only thing we have horizontally. So FGX, and that equals what? Well, remember, they used to equal 0 when we had balanced forces, but there's nothing going to the right here on the positive x direction to balance out the FGX in the opposite direction. So that means that's unbalanced, and that means our summation here is MA. So we only have one force, and it is FGX, and it is equal to MA. Now, we know that. The Y, I'm going to go ahead and write out the Y summation just because I can. So the Y summation, we have Fn plus FGY, and that equals 0 because that is balanced. So we have balance in the vertical. We do not have balance in the horizontal. Hopefully you see and understand what I'm saying there. Next, because at this point we haven't figured anything out. We have no numbers figured out, no quantities of any of these variables figured out. But we do know the mass of the block. So if we know the mass of the block, then that means we know Fg. So Fg is mg, yeah? Where m is 10 kilograms. Oh gosh. M is 10 kilograms. And g, of course, is 10 newtons for every kilogram, or 10 meters per second squared. You can view it any way you want. Now, here's what I'm not going to do. I'm not going to put a negative on it. Now, why would I not put a negative on it? Because the Fg here is off axis. It's not actually on the negative y axis. Fgy is. Fgx is actually negative x direction, but the Fg itself is not on an axis and therefore doesn't have a sign. It has an angle. It's 30 degrees on the negative side of the negative y axis. You could say that it is an angle of 240. You could say from the positive x-axis all the way around to Fg, it is 240 degrees. And so I'm not even going to bother putting a sign on it because of that. So that is 100 newtons. All right, Fg, 100 newtons. Now, we have a triangle here with our parts. We have a Fgy and an Fgx and a hypotenuse that is 100 newtons. So, and this is getting to be a mess already. Probably should redraw that triangle somewhere out here that makes it a little clearer. All right, so I have 100 newtons right here as my hypotenuse. I have, let me change the color here. I have Fgy right here, and I have Fgx right here. So that's my triangle, and of course this is the 30 degrees right here. So if it helps you all to actually re-sketch the triangle, oriented a little more normally, then by all means do that. Now what I'm going to do here, even though we don't need both, because again, there's nothing that's going to help us right now in the y summation. Like, we don't need any of these because there's no acceleration going on here. We're looking for acceleration, and acceleration is in this summation. So that's the force we need. We know the mass already. We need to know the Fgx so that we can find out what the acceleration is. So we don't need any of this stuff yet, but I'm going to find Fgy anyway because we have the triangle already here and ready to go. So Fgx, since that's the side opposite the 30 degrees, that's going to be the sine function. So I would say that sine of 30 is the is the opposite, or Fgx, over the hypotenuse, which is 100, which makes my FGX. This screen is terrible. 50 newtons. Jiminy Christmas. And so, I'll get this out of here. And so the FGY, oh man, this thing is, oh boy. This is cosine because it's the side adjacent to the 30. So I have cos of 30 is the adjacent, or FGY, oh my gosh, over 100 newtons, the hypotenuse. Oh my gosh. And that makes the FGY, oh my gosh, this thing, FGY is, oh my, this thing is a piece of junk. 86, and I'm going to run out of space, 86.6 newtons. Oh my gosh. And that's actually, now that I'm thinking about it, let's get this the signs identified correctly here, because notice in my triangle the FGY is in the negative y and the FGX is in the negative x direction. Do not forget the signs here. I already did. So negative 50 here. Oh my gosh. Sure, negative 50 there, and negative, oh Jiminy Christmas, I don't even have room for it. All right, and I can't even erase. Are you kidding me right now? Okay. Negative, there we go. It looks like it's not a negative. So anyway, negative 86.6 newtons, negative 50 newtons. Those are the two components. Now again, I only need the one. So if I go back here to my summation, I say that negative 50 newtons right here equals 10 kilograms, mass of the block, times A, my acceleration. And that means, obviously, my acceleration is negative 5. Now again, notice the unit of measure. It's going to be a newton over a kilogram, which we found out earlier in our Newton's second law labs that we did, the two-part labs, or lab that was two parts, that is a meter per second squared. So that is our acceleration of the block down the ramp with no friction force. Now, what if there is a friction force? What if there is a friction, a coefficient of, oh my, of 0.25. Oh my gee many Christmas here. This is terrible. There. All right, so 0.25. What if there's a mu, or coefficient, of 0.25? How does that change things? Well, that changes things by putting a friction force now in our scenario. So the friction force in this case is acting opposite the direction up the ramp here, up against its attempt at motion. So you need a new force diagram, or at least just add to it. I'm just going to add to it because I can. And so if I just, now here's the question, how big do you think that force is? I'm going to say that it's not as big as the FGX, because if it is as big as the FGX, then we don't have acceleration, it's just going to sit there. So that would be, I think, kind of obvious that we can't have an acceleration if the friction force, which I didn't even label, that is now a force of friction here. If we have a force of friction, it can't be as big as the gravity force in the x direction, or we don't even have the block able to slide. So I'm going to assume it's smaller in my diagram. Now, how does that change my summation? Well, my vertical summation doesn't change at all. The sum of forces in the y doesn't change because I still have the FGY and I still have the FN. Those are the only two forces I have in the y direction. But now, instead of only having an FGX, now I have a force of friction as well. So let me do that here. Let me just sketch that over here. So now my summation is, in the x, I have a FGX and I have an FF, and that equals MA. Now, we already know FGX. That has not changed. We already know M. That has not changed. What we don't know is the FF, or the friction force. Now, we have a way of calculating it because you did a lab on that as well. And so do you remember how to calculate friction force? Friction force is mu times Fn. Remember? Do you remember that? If you don't remember that, you should remember that now. So mu Fn is how you calculate friction force. Do we know those things? Well, let's see. We know that the mu is 0.25. We have that. We know the normal force. Well, do we actually know the normal force? Well, kinda, because we found out that the FGY was negative 86.6 newtons. We found out this was negative 86.6 newtons. Let me write that in there. Let me write that in here. Negative 86.6 newtons. And that equals 0 when you add it to the Fn, which makes the Fn what? Positive 86.6 newtons. Got that? So the Fn is the opposite of the FGY, which is now positive 86.6 newtons. So we do know that, and that goes in right here. Hopefully you're still following. Which means now I have my force of friction is 0.25. Oh, this thing is not cooperating. 0.25 times my 86.6 newtons of my normal force, which equals, oh, I wrote that down somewhere here. We're at 21 point, no. Yes, 21.65. All right, so that's 21.65 newtons. 21.65 newtons. That is my friction force. Now, what direction is that? Well, look back at your diagram. That is going this way, positive x direction, so that's going to stay a positive. Well, now what? Now, go back to the new summation we just wrote out, the FGX plus FF. I was gonna do this part on a whole different slide, but I changed my mind, and I hope that wasn't a bad idea because this is kind of a mess. But I hope you see. I mean, this we just, oh boy, oh my gosh, this thing almost. So this again, just a little sidebar here of where to find the components. We've still got our regular old force diagram, which we had to alter when I changed the parameters, saying that there is now a known friction force, or I should say a known coefficient of friction, which we can then find a friction force from. So again, I hope that you're following the thought process and the steps kind of along the way, because there will be a problem on this worksheet where you do it once where there's no friction, and you do it again and there is friction. So kind of like what we're doing now, but the problem is a little different than this. So anyway, back to, we found out the FF. We already know the FGX. That's the same as it was before. FGX has not changed. And FF, we just now found. So we just start plugging in our stuff then. So we have negative 50 newtons of FGX plus, oh boy, plus 21.65 newtons of friction force equals M, or 10 kilograms, times a, my acceleration, which I'm trying to find. This stuff equals negative 28 point, what did I, oh gosh, 35, is that right? No, yeah, 28.35 newtons, and that equals 10 kilograms times A, and so A equals negative 2.835 meters per second squared. So, hopefully you see this. Hopefully this makes sense, and this is how you would then approach an inclined plane problem with unbalanced forces. Again, all of what we're doing here is exactly the same as it was before, pre-unbalanced. Only now we're saying, hey, we have an imbalance. There is an acceleration. Because see, in times past, if you remember, the FGX and the friction force, those were the same amount because we summed to zero. Because it was either sliding down with a constant velocity or it was not moving at all. That's what our parameters were before, and that told us that our summation had to equal zero, which means the FGX and the FF were always the same. Well, now they're not. Clearly, they're not. So whenever your friction force is not the same as your FGX, you are going to experience an acceleration, and then this is how you would find out what it is. Now again, vertically, we still have balance. So the Fn and the FGY, that's still going to be balanced because we don't have acceleration happening in this dimension. We have acceleration happening in this dimension. And notice the sign on, oh, I didn't even do a motion map. And expert problem solvers do motion maps. Oh, notice that our acceleration is negative, which is this way. And our motion map, if we had drawn one, I'm going to go ahead and put, oh boy, I guess it didn't really matter. I can say that here's my zero, up is my positive direction, and that this object is starting out here somewhere and getting slow, and then getting faster, and then getting faster, and then getting faster, which makes my A this way. How about that? Yeah, is there anything else I can put on this screen to make it more confusing and jumbled? Let me think. Is there something else I can put on the screen? I don't think so. I think that's about it. So anyway, I hope that this helped. I hope I didn't confuse you. Yeah, I guess just go back and listen to it again. Hey, I guess that's probably better than just being in class and I say it one time and then it's gone and then you leave class and you forget about it. Well, now you can go back and listen to this thing as many times as you want. In fact, if you have trouble sleeping tonight, just pop some earbuds in and let my voice just soothe you right to sleep. Now, to conclude the video, let me grab another little sip of coffee here. Oh man, Tanzanian pea berry I just roasted last night. Absolutely fantastic. And yes, I am wearing my tie, just in case you were curious about it. Well, hey, this is Mr. Dillbone signing off. I hope you enjoyed the video and hope it taught you something worthwhile. I will be posting on Classroom which problems I want you to do for the next part of the assignment, and then we'll work out a way for you to actually turn that in as well. So, hope things are going well for you. We'll see you at some point, I'm sure. Bye.